Hello everyone, it's Benny, and welcome to the lighting section. In this video, our topic of discussion is pretty simple, pretty straightforward. How do we create realistic lighting with a computer? And, well, the obvious answer to that is, well, if you want it to be realistic, just do what reality's doing. And that's true, if you do what reality's doing, you will get perfectly physically accurate, realistic lighting. But there's a bit of a problem with that, because what reality does is it sends hundreds of trillions of photons bouncing all around the room, and then, whatever the sum effect of that is the end result of the lighting. And you can't really simulate that real time with a computer for obvious reasons. There's hundreds of trillions of particles. You're going to have a tough time simulating all of that in real time. So, we're back to the starting question. How do you achieve realistic lighting with a computer? And for the longest time, the answer to that was you can't. You can't achieve realistic lighting with a computer because what reality is doing is too complex. And that's why for the longest time, you never saw any lighting effects of computers that looked very real, even in pre-rendered applications. Well, that is until about 1986. Because in 1986, there were these two people whose names I'm going to horrendously butcher. Their names were David Immel and James Kajia. They had an idea. And they thought that, there must be some way to still get the physically accurate sum of what lighting does without simulating all the particle nonsense in between. And their idea was the law of conservation of energy. They thought, if we keep track of the way lighting energy moves around the room, maybe there's a simplification to this. Maybe we can still get the effect of what light does without actually simulating the lighting itself. And, after a lot of physics and a lot of math, as it turns out, they were right. And the end result of all their labors was what is arguably one of the, if not the, single most important equations in all of computer graphics. And that is the rendering equation. It, using some comparatively straightforward math, gives you almost completely physically accurate, realistic lighting. And when I say almost, it really is pretty much physically accurate. The few things it doesn't simulate are extremely minor. I mean, it doesn't simulate things like interference patterns, so you can't do a physics experiment with it. It doesn't simulate the relativistic Doppler effect, so sorry for people who want to simulate relativity. And I guess the biggest thing it doesn't simulate in the direct form is refraction, but that can sort of be added on, so that's not even really that much of a minus. So yeah, it's pretty much the holy grail of lighting, in a sense, because it gives you pretty much a completely physically accurate idea of lighting, well, almost, and it does it using some comparatively straightforward math. In fact, this little scene I've got showing here was drawn with maybe not the exact rendering equation, but at least a pretty good approximation of it. So, and this is just drawn with the rendering equation itself, so no fancy things added onto it. As you can see, you get pretty much exactly what light does. You get it's the fact of like, hey, light doesn't always reach the corners perfectly. You get shadowing straight up. You get accurate reflections. You get, again, really, really accurate idea of physical lighting with the rendering equation. So that's essentially our answer. It's also essentially everyone's answer. The rendering equation is the basis of all lighting in computer, well, pretty much all lighting in computer graphics ever since then. Extremely important equation. So now that I've talked all about that, I'm going to start walking you through the rendering equation, showing you, writing it out for you, well, first off, and then showing you how we can work it to get realistic lighting in our game engine. Now, before I go ahead and write it out, I'm going to make two relatively straightforward simplifications to it, just to get rid of some stuff that isn't really relevant to the way we're using it. First thing is, I'm not going to be including the time term in the equation. And the reason that's there in the original rendering equation is because maybe you have some light that's fluctuating, maybe you have like a bulb that's sort of flashing on and off because the power's not working right. And that's something you might use a time term for. You might animate that with respect to time. But since I'm using this for a game engine, well, in our game engine, all of our updating is already done before the rendering phase happens. So essentially, the light's already at whatever phase and fluctuation it's going to be at before I even start calculating what the light should be. So I don't need to worry about it because it's not going to be continuously changing when I calculate the equation. So yeah, I'm going to just drop the time term because we don't need it for our application. And second thing I'm going to get rid of is the frequency term, because the rendering equation isn't just for lighting. It's actually for the entire electromagnetic spectrum. So you could calculate how an X-ray bounces around your scene and get X-ray vision if you really wanted to, but I'm not really going for that. I'm just going for lighting. So I'm going to just drop the frequency term, since the way we're going to end up using it is we're going to calculate the red amount, whatever frequency that is, the green amount, whatever frequency that is, and the blue amount, whatever frequency that is. So we don't need to worry about it, because we're not going to have a bunch of different frequencies. We're only going to calculate it for 3 frequencies, I guess, and that's it. So yeah, those are the 2 simplifications I'm going to do right off the bat. If you want the full version, you can look on Wikipedia. It's a good resource for that. But yeah, I'm just going to drop those because we don't need them for our purposes. So first up is the left-hand side of the equation, what the rendering equation is actually calculating. And that is the light that is being output from some point that I'll call X in some direction I'll call W. So it's calculating the amount of light that's coming out of some point in some direction. And the way we'd end up using this is we'd calculate the amount of light coming from each individual pixel, so those would be all the points, in the direction that's coming towards our eye, our camera. That's the way we'd end up using this. And yeah, that's the first term. And this is calculated by the amount of light that is emitted from this point in this direction. At least that's the first thing, because that way, if it's something like a light bulb, then hey, that light bulb is emitting some light. So I'd first off just take into account whatever light is being emitted at me from that direction. So yeah, and then I add that to all the rest of the equation. And this is where the equation gets a little bit tricky, because for the rest of the light, it uses an integral. And the reason this is a bit tricky is because it's an integral. It's not your typical integral. It's an integral with omega. And oh god, that's a terrible omega. Oh well. Point is, it's taking an integral of the omega, and what that means, at least in the context of this problem, is it's taking into account every single direction of light in sort of a sphere around this point. So if you imagine this is a sphere and this is our point, it's just taking into account every single direction coming towards our center point, if that makes any sense. So yeah, that's the whole point of this integral. And in this sort of integral, the first term in there is the amount of light that's coming in from, well, coming in towards this point from some direction W prime. And that sort of represents whatever direction I'm currently looking at in the integral. So this represents the integral, all the different directions I'm looking at. If I'm currently calculating light from this direction, this would be W prime. If I'm currently looking at it from this direction, that would be W prime. This direction, that's W prime, etc., etc. So yeah, that's what W prime is. And that's that's the first thing I'm going to look at in the integral. The amount of light that's coming towards this point from whatever direction I'm currently looking at in the integral. And at this point, we've actually got most of the equation written out. There's only two more parts to it, but they're both a little bit tricky to understand if you've never dealt with lighting before, so I'm going to walk you through it. So for our first example, it's an effect called attenuation. And it goes a little something like this. Let's say right here is me. Oh dear. Well, yeah, that's me. And I'm looking at some surface right here. And in this area around me, there's two lights. There's going to be one here and one here. Light A and light B. So if I turn on light A, then light A is going to be going this way, going to hit this surface, and then come back to my eye, so I can see it. Light B, if I turn that on, it's going to reflect, going to go to the surface, and come back to me so I can see it. Now, here's the thing. If I turn on light A, then turn it off, and look at light B, which one's going to be brighter? Which one's going to illuminate the surface more? If I turn on light A, is the surface going to be brighter then? Or is it going to be brighter when I have light B on? You don't know? Let me put it another way. Let's say this is a mirror. I'm turning both lights on. It's reflecting light A right back into my eye. It's reflecting light B into my eye. It's sort of a glancing blow. Which one's going to be brighter? Which one's going to cause my eyes the most pain? If you guessed light A, you'd be correct, because light A is reflecting pretty much directly right back into my eyes. Almost. And then light B, it's, like I said, reflected a little bit of a glancing blow, so since it's not reflecting directly back at me, it's going to get, not as much light. And this is a phenomenon known as attenuation. And the way you calculate this is with, well, first off, whatever direction the light's coming from, so W prime, and the normal, whatever direction is up in the surface, because if it's going in the same direction as whatever direction is up on your surface, which is called the normal, then that's when it's reflecting directly back. If I have light that's that's reflecting directly back from the normal, then, well, there you go. That's when it's getting the most direct effect. But, on the other hand, well, you get the idea. That's how the normal's involved. But yeah, so it's reflected the glancing blow, not as same thing I described earlier. But yeah, so that's how the normal's involved. That's its relationship to W prime. Now, to achieve this effect in our equation, we're going to have to multiply our incoming light by whatever attenuation it receives when it reflects. And here's how you calculate that. First off, you're going to start with W prime, the incoming light direction, but you're going to make it negative because attenuation is based on the direction light's reflected, not the direction it's coming in. And I'll sort of emulate that. It won't give you the true reflected direction, but it'll give you the information you need. So you'll take the negative incoming direction and multiply that by the normal using a dot product multiply. And since the dot product is the application of one vector to another, so it's how much reflected light is going in the normal direction, essentially, then that will give you the attenuation. And you multiply the attenuation by the amount of light incoming, and congratulations, you've just successfully calculated the attenuation. And there you go. So now we only have one term left. Well, not term, one part of the equation left. And this last term is something called the bidirectional reflectance distribution function, or BRDF. So, you might be wondering, what's a bidirectional reflectance distribution function? And this, like many impressive sounding terms, is actually something that's really not that complicated, with a really technical sounding name. The bidirectional reflectance distribution function is essentially just how a surface reflects light. It's sort of just a catch-all term for that. So for example, maybe the surface reflects certain frequencies better than others. That creates a phenomenon we know is color. So color is part of the BRDF, it's part of how a surface reflects light. Another thing is maybe, hey, some surfaces are more reflective than others. Some surfaces are very shiny, other surfaces are not. That's also part of the BRDF. So it's essentially all the material properties of reflection. So things like I said, those are really the big stuff. Color and shininess, those are the really big parts of the BRDF. And it sort of warrants its own discussion, but that's sort of the idea. It's things like color, shininess, just material properties. Things that have to do with how the surface reflects light. So yeah. And that's the final part of the rendering equation. So, to add this to our equation, I'm sort of running out of room, so I'll just do a little dot here, times this new function, which I'll call f of r for function of reflectance. So our BRDF at whatever point we're calculating at, in whatever direction we care about, taking into account whatever direction light is incoming. That's why it's bidirectional. Because it takes in two directions. The direction that we care about light coming out of, and the direction light's coming in. So yeah, that's the BRDF in this giant equation. And finally, we have to finish our integral term. So, our integral in this hemisphere with respect to w prime. And that's it. That is the rendering equation. It's big, it looks a little complicated, but this is the equation. This is the equation that generates this. It's the equation that serves as the basis for pretty much every lighting effect in computer graphics. And yeah, there you go. So, now that we know what the equation is, how do we, use it? How do we calculate it? How do we take this equation and make it into something that can be used in our game engine to actually calculate lighting? Now, you could try implementing the equation directly, but there's a few issues with that. The most obvious being this integral term. How do you calculate an integral in, say, a fragment shader? Yeah. So, our game engine isn't going to implement the rendering equation. It's going to implement an approximation of the rendering equation. And depending on how you approximate the rendering equation, you get different, relatively well-known rendering techniques. If you do certain optimizations, or not optimizations, if you do certain approximations, you'll get the radiosity rendering technique. If you do certain other approximations, you'll get the ray tracing rendering technique. So yeah, depending on how you want to approximate this, you can get a vast, vast variety of different rendering techniques. But here's the big simplification I'm going to do. You see, this integral term, which takes into account the hemisphere, all light that's coming in from all directions, is, well, it's taking into account all light coming from all directions. And that's great if you want indirect lighting, but indirect lighting isn't the most significant lighting effect of all of them, really. So, instead, I'm only going to take into account direct lighting. I'm going to only take into account light that's directly reflected from some light source. And that does lose a little bit of approximation. Not much, though. The biggest loss here is probably shadowing. But, yeah, it's probably the easiest way to just get rid of this integral term and make this still perform. Well, I shouldn't say still, but just to get rid of the integral and make it perform nicely. So, let's rewrite our rendering equation. I'll just draw sort of a line here. And let's start writing out our approximation. So, the light emitted from some point in some direction is, first off, I'm going to drop the light emitted term entirely, because I'm not going to be emitting light from pixels in my game engine. I'm going to be having actual objects which act as lights. So I don't even need to take that into account. I'm just going to drop that term entirely and just go straight to this. So I'm getting light from some other external objects that I'm going to be implementing later. And this is going to be a sum, because I don't have an integral anymore. I just have the sum of all the different light sources. And for the sum, it's going to start, of course, at I equals 0 to k, where k is the number of lights that I have. And then I'm going to do pretty much the same thing, because I shouldn't have a problem from there. So it's going to take in the amount of light that's coming in, 2x, from some direction, w prime, and I'm going to multiply that by the attenuation, because again, that's not causing an issue, times normal, and then there's the BRDF. How do I take into account all the material properties of something being reflected? And there's a lot of different ways to do this. For now, since it's all I have in my game engine, I'm just going to take into account one thing for the BRDF. C, the color. And there you go. That's all there is to it. This is going to be our approximation for the rendering equation. All we've really done is we've dropped the integral, which takes out all the indirect lighting stuff, and now we're only taking into account all the light coming directly from light sources. It gets us a lot of accuracy here. We're taking into account our BRDF, which, granted, is a little simple right now. We'll fix that a little bit later. And it has perfectly accurate incoming light, so because that's exactly as it is in the rendering equation, and perfectly accurate attenuation, because that's exactly how it is in the rendering equation. So all we've really approximated here is the BRDF, which we'll improve a little bit later, and indirect lighting, which we've just dropped entirely. So we'll need to do something a little bit different for that when we get to it. So now let's talk about performance, because, you know, we're trying to do real-time rendering here. Performance is pretty critical. How does this equation perform? How does this approximation mean? Sure, it's a decent approximation of the rendering equation, but can it still be done in real time at a decent rate? And for the most part, the answer to that is yes. Attenuation is a basic multiply operation, nothing fancy there. Getting color, again, basic multiply, nothing fancy there. Two multiply operations, I mean, who can't do that? And then, the thing that might get a little kinda sorta tricky is the light intensity from some point. But for the most part, that's just going to be a property of the light. The light's going to have some intensity, and that's going to be it. So, again, that's just essentially going to be a multiply operation. So 3 multiplies. Yeah, that's not a lot. Calculating the equation itself is not going to be much of a factor in the performance of this. It's going to be pretty solid performance overall. The two things that are really going to hurt your performance are, one, the number of lights. Because, as you see, this is a sum. It's not just a straight 3 multiplies. It's 3 multiplies times however many lights you have in your scene. So, If I have 20 lights, it's not 3 multiply operations per pixel, it's 60 multiplication operations per pixel. You know, if I have a bunch of laser guns and they all have their own lighting, then that could be hundreds and hundreds of lights all at once. And that results in possibly thousands of multiplication operations per pixel. That can cause a little bit of a problem. So you want to be very careful with the number of lights. And in fact, a little bit later, we're going to be talking about how we can minimize this, because just implementing this straight as it is, the single biggest problem you'll probably run into is every single light in your scene has an effect on every single object in the scene, no matter where it is. So if I create this tiny little spark half a kilometer away from where I am, I'm still going to be calculating the effect of the light that spark gives off, even though it's just ridiculously far away from me. It can have a completely negligible effect. So, yeah, we're going to be doing some things later to minimize that effect. But overall, it's still going to perform pretty good, because even if I have 4 lights in my scene or something, which is realistic, if I have 4 or so lights or something, that's still 12 multiply operations per pixel. That's not going to be a huge deal. So that's the first thing that's going to cause some problems. The other thing that might cause issues is your normals. How are you going to get the normals in? And that sort of warrants almost a discussion of its own. Now, I'll just go ahead and tell you the way we're going to end up eventually doing it is we're going to be storing the normals in all of the vertices. And what we're going to end up doing is we're going to end up using interpolation, the interpolation feature of the graphics card, to figure out the normals for the rest of the surfaces. But you can do this a lot of different ways. One way you can do it is you can do normal mapping, which is essentially have a texture where instead of having colors, each color is actually a normal vector, telling it, hey, if you map this to the surface, it tells you where all the, where the surface is up. And you get a lot of really interesting lighting effects that way, but I won't be doing that yet, I should say. So there's a lot of ways to handle the normals, and depending on how you handle it, you can get some expense in figuring out the normal. But it shouldn't, it's one of those things which really shouldn't be overall a huge deal. So overall, this approximation right here is a really, really good contender for real-time lighting. It's what almost every game engine uses, at least in some form or another, for real-time lighting. This is a method called diffuse lighting, and it's probably one of the most prominent and one of the most effective lighting techniques for real-time lighting there is. So yeah, that's going to be our first method of doing lighting in real time. We're going to do a few more things later, but yeah. So hopefully you enjoyed this video. I want to just cover not only what our lighting technique that we're going to be using is, or at least our main technique. We're going to do a few things after this, because this isn't going to be quite enough. But yeah, I wanted to share what the main technique is, and I also wanted to show you just where it comes from. I know I didn't actually manually derive the rendering equation. If you want that, I'm sure someone's done it somewhere on the internet that you can look up. But yeah, I want to show you that this doesn't come from nowhere. It has a basis in reality, and this is what we're going to be using. And hopefully now you know about some of the performance pitfalls you might come into with using this, and where it falls short, because for example, it doesn't take into account shadowing. If you want shadowing, you're going to need to do something a little bit different. So, yeah. So yeah, there you go. That's all I really wanted to cover in this sort of introduction to lighting. Trust me, we're going to be talking about a lot more about this later on. So, thank you, hope you enjoyed, hope you learned, and see you next time.